Okay, so as mentioned in the email this video is attached to, a 15 kilogram uniform ladder leans against a wall in the atrium of a large hotel. The ladder is 8 meters long. It makes an angle of 60 degrees with the floor. The coefficient of static friction between the floor and the ladder is mu sub s is equal to 0.45. How far along the ladder can a 60 kilogram person climb before the ladder starts to slip? Assume that the wall is frictionless. Um, the first thing I did here was make a pretty careful drawing of the ladder and label all the distances and forces that were involved. And what I did here was draw a few different diagrams instead of cluttering them. Instead of cluttering all of them together with numerical values, I used L for the length, and that is equal to 8 meters for the length of the ladder, and D for the unknown distance from the bottom of the ladder to the point where the person stands. M was equal to 60 kilograms, and that was M, capital M, and the smaller m is equal to 15 kilograms. Now for the masses of the person and the ladder, respectively, the weight of the ladders acts as the ladder's center of gravity, and again that's the ladder's midpoint since it's in uniform. Now knowing all that, I was able to apply the conditions for the equilibrium, starting with the sum of the forces in the x direction equal to 0. I was able to find that N sub W minus F is equal to 0. Let me scroll down here so that you can see that. And now this is where, if the climber is at its highest point possible, the frictional force must have its maximum possible magnitude. And then that gives me this formula here, which is F is equal to mu sub s times N sub F. And now I was able to combine these two equations and attain a relationship between the magnitudes of the normal forces. And that gives me this equation here, which is N sub W is equal to mu S times the N sub F. And then I moved on to the next condition, which was the sum of the forces in the y direction equal to 0. And that gave me the formula here of N sub F minus capital Mg minus Mg is equal to 0. And the only unknown quantity in this equation is N sub F, so I was able to solve for it. And I get that N sub F is equal to capital Mg plus Mg is equal to M, capital M plus M times G. And now I was able to find the other normal force because of this, and I set the equation of normal force sub W is equal to mu sub S times N sub F is equal to mu sub S times capital M plus lowercase m times G. And at this point I have all the expressions for the magnitudes of all the forces, but the only thing I don't know is the distance, which is the entire goal of this problem. So in order to find distance, I had to set the net torque equal to 0. And we'll come back up here so we can look at my diagrams again. And the first thing I did was choose a rotation axis. And I found the most convenient choice is an axis that was perpendicular to the plane, and it passed through the bottom of the ladder. Well, since two of the 5 forces, those two being N sub F and F, act on the bottom of the ladder, these two forces have 0 level arms, and therefore they produce 0 torque. But another reason why this is a convenient choice of the axis is that the distance d is measured from the bottom of the ladder. So in this situation we have here with the forces either vertical or horizontal, I thought it was easiest to use lever arms to find the torques. So in my 3 diagrams right here, I first drew the line of action for each force, and then I drew the lever arm that it was perpendicular distance between the axis and the line of the action. But using the usual convention here, that counterclockwise torques are positive, and that the torque due to the N sub W is negative, and the torques due to gravity are positive. I got the magnitude of each torque is the magnitude of the force times its lever arm, which was this equation. For the torque is equal to Fr perpendicular. And now again, this is setting the torque equal to 0 yields this equation right here, which is negative N sub W times L sine of theta plus Mg times 1/2 L cosine of theta plus Mg d cosine of theta, and again that's all equal to 0. Knowing all this, I was able to solve for d pretty algebraically. with my formulas here of negative n sub w times L sine of theta divided by mg cosine of theta plus 1/2 mg L cosine of theta divided by mg cosine of theta plus the distance, and again that is all equal to 0. Now here I have my distance equation, which is equal to n sub w times L tangent theta divided by mg minus m sub L divided by 2m. And for this next step I substituted n sub w, and I was able to get the equation here, which is d is equal to L times mu sub s times m plus m times tangent theta divided by m minus m divided by 2m. And after manipulating this formula and plugging all my values in, I get my value out that he can stand up to 6.8 meters without, and then if he goes any further than that, the ladder will slip. But this is the distance along the ladder, and it's not the height above the ground, which I solved for the height here, which is very simple compared to the rest of the problem. And I get that h is equal to 6.8 meters times the sine of 60 degrees, and the height above the ground would be 5.9 meters.